Started recording.
Okay, great. Hi, welcome everyone. Welcome to the quantum session 7B of STOC. So just real quick, so the format is every paper gets 10 minutes, so 5 minutes for the presentation and 5 minutes for Q&A. Please save your questions. You can type your questions into the Q&A. And they'll be answered during the Q&A session. And then after all the talks are over, at 11:40 Eastern time, we'll have 20 minutes where we can just have a free chat over Zoom with the speakers. So, first up we have Anurag Anshu, who's going to tell us about entanglement subvolume laws for 2D frustration-free spin systems. So Anurag, if you can share.
Hey, Henry. Yeah, thanks. The sound is clear, I hope?
It's very clear.
Yeah, great. So I'm going to share my screen and let's get started. All right, just one sec. Okay, hi everyone. Thanks for joining. This is a talk. Oh, so there's a question in Q&A. That was fast. Okay, I'll just go ahead with my talk. All right, so this is based on a joint work with Itai Arad and David Gossett, and the key characters of this talk are going to be local Hamiltonian systems, which are a collection of spins. I'm going to assume in this talk that they live on a square lattice like this, and these spins are interacting, and the interaction, it's defined by a Hamiltonian, which is a sum over these local terms Hij. You can think of each of these Hij as acting on a small collection, let's say 4 of these spins, and each Hij corresponds to a placket. For the classical people in the audience, you can think of local Hamiltonian systems as quantum versions of the constraint satisfaction problems. An important question, both from physics and also quantum complexity point of view, is to understand the entanglement entropy of the ground state of the Hamiltonian. What it means is that you look at your square lattice and you divide it into 2 parts, let's say A and A complement, and you ask what's the entropy of this region, where entropy you can define in a manner similar to the way you define classical entropy. There are a few terminology. For example, you say the ground state satisfies an area law if its entropy scales as the area of the region. A volume law is the easy one. It says that the entropy scales as the square of the area or the volume for 2D. And subvolume law is the intermediate region. Our result is that ground states of something which I'll describe quickly satisfies a subvolume law with power 5/3, which is more than 1, but less than 2. By gapped, I mean the difference between the lowest energy and the second lowest energy of the Hamiltonian. Locally gapped would mean that the Hamiltonian in every subregion is gapped in a certain subregion. And frustration-free means that that the ground state satisfies all the local terms, similar to the satisfying assignments of the constraint satisfaction problems. All right, so a series of important prior works, they laid out the foundation for how to go about proving these area laws. And the upshot of these works was that better polynomial approximations prove better 1D area laws, where you approximate the ground state by polynomials of the Hamiltonian in some proper choice of norm. And if you can do that in a good way, then you're able to prove good area laws. The issue was that these results, even the best known Chebyshev polynomial, still would give a volume law in 2 dimensions. That is, it would not give the desired subvolume or area law behavior. And just to clarify, what I mean by best known is that if you look at the polynomials of the Hamiltonian, then the Chebyshev polynomial is the polynomial that best approximates the ground state for a fixed degree. And for people who are aware of technical aspects of this, it follows because the Hamiltonian has a continuous spectrum. So Chebyshev does the best in approximating the ground function. All right, so our starting point is the observation that in the specific commuting case, you can in fact prove the area law, unlike these trouble in the prior work, which could not prove area law for a general case. You can prove area law using a better family of polynomials. And for the quantum algorithm fans here, you might recognize these polynomials as coming out of quantum theory complexity of AND function, which turns out to be square root of log 1 over epsilon instead of root n times log 1 over epsilon. Like the log 1 over epsilon is inside the square root. For the approximation theory fans, you might be aware of these better polynomials as those that approximate the AND function with this kind of error instead of the error of d over root n, which might come from Chebyshev approximation. To be honest, both these fans are the same crowd, but I believe you might see these things differently. All right, so our method is that we first we look at these polynomials and we give different constructions of these polynomials, which is kind of based on using local approximation to build global ones. This construction turns out to be quantum friendly, and before that, let me describe the key component here. We use a robust property of the composition of these polynomials, which was shown by STOC in 2013. And what we do is that we combine with some known techniques for ground states for local Hamiltonian system. Combining these ingredients, we construct these polynomials up to some extent in the local Hamiltonian setting. And the error in these techniques for the local Hamiltonian system leave us at a middle ground. We don't get to area law, we get to subvolume law, but we go beyond volume law. All right, that's it. Thanks for your attention. I'm ready for the questions.
Great. Thanks for the presentation, Anurag. So if there are any questions, you can raise your hand in the Q&A, and I can promote you to panelist or unmute your microphone.
Oh, there's a question. Do you have any insight into, so Mehdi asks, do you have any insights into whether your construction implies a method for efficiently contacting the dense network? We are not sure. I guess the first question would be whether you have an efficient way to represent ground states using tensor network. We even don't know that, but we do expect that something like further investigation might tell us more. Next question is there an intuition why you can only get a subvolume with power of 5/3 instead of volume law? Well, 5/3 is not the most, I mean, I don't have a good intuition about the ratio 5/3, but what I can tell you is that we end up being somewhere in the sort of middle, or like 1/3 of the way. And that happens because of the error that comes from detectability lemma. I expect 5/3 to improve further, but in the current techniques, I don't expect to go beyond, to go all the way to area law. We need something more to, get the full behavior. Oh, sorry.
So Anurag, I have a question. Can you say a little more about this frustration-free assumption? Like, is it very essential? And like, where is it used in your proof?
It's used in the detectability lemma. This result in this prior work. It applies to the case of frustration-free systems. It may be possible to generalize these things to a frustrated case, but there are some techniques by Hastings which kind of convert a frustrated system to a frustration-free one. But I mean, I feel like a bottleneck there is to get rid of the local gap assumption. Once we are able to do that, we should be able to generalize these things to a frustrated case as well. Does it make sense?
I see. Right. So there's a question.
Why physicists or TCS folks care about these laws? Because, so I skipped important aspect of proving these area laws is that at least in the one-dimension case, area laws are pointers to states which have efficient representation. And this is interesting from the point of view of quantum complexity theory, because number one, ground states play the same role as satisfying assignments of, 3SAT, for example, plays for classical complexity, so ground states play the same role. And second, the guarantees to obtain efficient representation of ground states is obtained by proving array laws, at least in one dimension. Two dimension, we don't know yet, so that's an open area of research. But in 1D, array laws kind of lead to efficient representation. Then you can classify these classes. Then you can put them in NP or P and things like that. And also you can use a lot of polynomials in these methods. So that's interesting. Right? People who work in theory of polynomials may find these things interesting as well.
Great. So I think that's it for the Q&A session. So maybe we'll move on to our next talk, which is given by Luke Shaefer. And he will tell us about interactive shallow Clifford circuits, quantum advantage against NC1 and beyond. So Luke, it's all yours.
Hi. So, right, I'm talking about interactive shallow Clifford circuits. This is joint work with Daniel Greer. So the prior work that inspired this was by Bravi, Gossett, and Koenig. So they introduced the hidden linear function problem and showed that it could be solved by constant depth quantum circuits, but not by constant depth classical circuits. So it was a separation between QNC0 and NC0. And this was subsequently improved by Bene-Watts et al. They showed that HLF cannot be solved by AC0 circuits. So you start to wonder what the right classical class is for HLF. Where is it among all classical classes? So Bravi, Gossett, and Koenig showed that it was at least in polynomial time, and we can improve that a little bit. We noticed that the quantum circuit that they use to solve the problem is actually a classically controlled Clifford circuit. And since it's known that Clifford simulation is in a class parity L, it follows that HLF is also in parity L. And parity L is this class of sort of linear algebra problems modulo 2. So determinant and inverse and iterated matrix multiplication are all complete for this class. And Clifford simulation is also complete for parity L. So maybe we conjecture now that HLF is parity L complete, right? Especially since we tried and failed to put it in natural smaller classes like L or NC1. So could that be? Well, suppose it was parity L complete under, say, AC0 reductions. Then you'd get this situation where a constant depth quantum circuit solves the problem. And with the help of the reductions, you could use that to solve parity L-hard problems. So constant depth circuits are being used to solve, say, log depth circuit problems or log space problems. And that's kind of concerning. So that seems unlikely. What do we do? Well, we switch to an interactive problem. And we start with a grid of qubits, all in the plus state, and apply CZ gates between them in constant depth to construct a cluster state. And then we measure the cluster state. So there's 2 rounds of measurement. First, we're told how to measure almost all of the qubits, with constantly many set aside in either the X or the Y basis. And then we return the answers. And only then we're told how to measure the remaining few qubits. And we get answers for them back. So from the outside, interacting with the device that solves this problem, it looks like this. We send bases over to the device, it provides outcomes. We send more bases over the device, and it returns more outcomes. And then maybe optionally, we can reset back to the beginning of the protocol and run all of this again. So this is something a constant depth quantum circuit could actually do, right? Splitting the measurement up into 2 phases is no big deal. But if a classical device were solving this problem, notice that we could open it up in the middle of the computation, look inside it, and clone the state. And then when we continue on and get to the end, instead of just resetting back to the beginning, we could go back to the state we cloned in the middle. And so a consequence of having this interactive problem is that whenever the classical device solves this simple problem, it's actually also having to solve this more difficult problem, or there exists a machine that solves this more difficult problem. And so that's the problem that we end up showing is parity L complete. Okay, we show that this rewindable version of the interactive HLF problem is parity L complete under randomized reductions. And so the takeaway then is that we have this problem that a constant depth quantum circuit can solve, but is, for classical circuits at least, parity L complete. So sort of the largest known separation, but with all these caveats. And that's all I have. Thank you.
All right, thank you very much, Luke. So are there any questions? I also went ahead and promoted everyone to panelists because you know, it's not that big of a session, and I think it's a nicer experience to have everyone see who else is around, and you can just unmute yourself and ask questions. So Mehdi, you're also free to use the microphone in video. Mehdi, are you there? Okay, so maybe I'll just read out his question. So he's asking, do you know to what extent your separation extends to noisy quantum circuits?
Actually, we have an intern visiting this summer that's working on that problem. So I don't want to get too much into the details and ruin his result, but he's thinking about that sort of thing, and I think it's going well.
I have I think a short question about the model. So you distinguish between like circuits with classical control and sort of not. And so like the QNC, when you talk about QNC0, is there like an additional layer also of like a classical control going on there or something like that? Or it's really just like a log depth quantum circuit and that's it?
No, it's even a constant depth.
Sorry. constant depth. Yeah, NC0. Yeah.
No, it's fine. We distinguish it for the Clifford circuit because it makes it because then we can apply these Aronson-Gottesman things. But a quantum circuit or a quantum gate with a control bit doesn't. I mean, it's still a quantum gate, right? If you just promote all the classical bits to quantum bits and make them part of your input, then it's just a quantum circuit on all those qubits. Do you see what I mean?
I guess. Yeah. I mean, I just haven't thought it through. Like maybe the classical control could be like a lot more complicated or something like that. But fine, if you say
yeah,
it's the
you
same,
could imagine the classical control having like power that the quantum device doesn't, like polynomial.
Well, like in the Clifford case, that's presumably kind of what's going on. The classical control is like more complicated than just like linear operations or whatever the classical equivalent of Clifford is.
Actually, it's literally just each bit of the classical input controls one of the gates, the quantum gates. It's just adding an extra control to a Clifford gate would make it non-Clifford, and we need to avoid that.
I understand. All right, thanks. Yeah.
Luke, hi.
Hi, Scott.
Yeah. So you presented your result in a very interesting way, that HLF is parity L complete in some sense. You know, so it occurred to me that one could likewise say, like, boson sampling is sharp P complete in some sense, right? Can we formalize what this sense is? That like, you know, there's this sense of completeness that only works if you have a classical simulation.
Yeah, that would be nice. I think they're slightly different reasons, perhaps, but formalizing either one would be awesome.
Well, yours involves an interactive protocol, right? But you know, they both really depend on, you know, you get a consequence, but only if the simulating algorithm is classical, right? And
exactly.
Yeah.
Yeah, I wish I knew.
Okay.
Any other questions? Okay, so thanks again, Luke. So if not, let's move on to our next presentation, which is actually a split presentation between Naihui Chia and Matthew Kudron, who will tell us about oracle separations between different quantum depths. So I think Naihui, you're presenting first, right?
Yeah.
Okay, so it's all yours.
Yeah. Yeah, thanks, Henry, and Harold, thank you for joining. And Matt and I will introduce our two works on the power of quantum depth. And this is a joint work with Kai-Ming Chong and Jing Lai, and this is another joint work with Matt and Sankis Manda. So our work is motivated by the fact that near-term quantum computers must have small 30 depths due to gap fidelity and coherence. So it is natural to ask the following question: is it possible that small depth quantum computer with classical computer can be as powerful as general quantum computer? So here, general quantum computer means like poly-n depth quantum computer that can implement all the polynomial time quantum algorithms. So you can view this as a hybrid approach. You have a small depth quantum computer and you have a powerful classical computer, and you can exchange classical messages between these computers and let them collaborate together to solve problems. And we want to see whether this hybrid approach could be equivalent to poly-n depth quantum computer. So our results in this tool show that actually there exists an oracle problem P such that P cannot be solved by poly-n depth quantum computer, but not log-n depth quantum computer plus classical computer. So actually we find this problem, which is in the outer circle about poly-n depth quantum computer, but not in the second circle of log-n depth plus classical computer. And actually the oracle problems we use in CCL20 and the CM20 are different. And Matt will tell you their oracle problem later, but I will introduce our oracle problem first. And also our oracle problem gives a sharper separation. We actually show that 2D plus 1 depth quantum computer is more powerful than D depth quantum computer plus classical computer. So I'm going to tell you the oracle problem. So our oracle problem is starting from the Simon's problem, because Simon's problem is very good. It is quantum easy, so it is in the outer circle, but classically hard. So it is likely to be outside the second circle. However, Simon's problem is actually too easy. It can be solved by constant depth quantum computer with classical post-processing. So we need to make the problem harder. So our idea is very simple. We try to make the problem harder by using pointer tracing and hiding. So for the pointer tracing, we mean, so our construction is like follows. We try to enlarge a domain to make the original to hide the original domain in a larger set. So this is called hiding. And then we will do shuffling. We will shuffle the Simon's function D times to make the function like too noisy for people to follow. So here's our construction. We will first have random permutations F0 to FD-1 in a larger domain. Those are just purely uniform random permutations. And for FD, which will be a function that encodes the information about the Simon's function F. So if your point is in SD, the real domain, then it will map it. It will follow the Simon's function to map it to SD plus 1. But if it is outside SD, so like TD, but not in SD, then you will just get both, which means no information. So our problem is as follows: you will be given the D-shuffling oracle F of the Simon's function. So here, D-shuffling oracle is that you have F0 to FD, and you can query that independently. And then you are going to find S. The problem asks you to find S as Simon's function. So this is our oracle problem. And yeah, so Matt will tell you the rest of the thing. Okay.
All right, thanks, Naihui. So I'll share my screen very quickly to show the last slide. Okay, so as Naihui mentioned, just sort of in conclusion, these results, actually the results of Naihui et al. Is able to separate interleaved quantum classical computation, where the quantum computation has depth 2D plus 1 from that same class where the quantum computation has depth just D. And our result is maybe a less refined separation between polynomial depth and log depth, or depth less than polynomial. And in both cases, for both results, this separation holds for two different computational classes, one corresponding to a conjecture of Jozsa and one corresponding to a conjecture of Aronson. And then there are some natural open questions that we wanted to mention. One is, so both of these results show an oracle separation between these bounded depth classes and BQP. But you could ask whether you could extend this oracle separation to a separation based on perhaps a cryptographic assumption. And so I believe actually Scott Aronson asked this question before. And then another question is if you could sharpen this depth separation, instead of 2D plus 1 to D, it's D plus 1 versus D. All right. And I believe that I'm out of time now. Yeah. So why don't we let it go to questions?
Great. Thanks, Naihui and Matt, for the hybrid talk. So any questions? Feel free to unmute yourself. So maybe while people are thinking of questions, I have one. So what are the prospects of showing an oracle separation between like noisy constant depth quantum computation of say depth 2D versus, yeah, you can either compare it with noisy depth D computation or noiseless computation. Have you guys thought about something like that?
No, but I think this is a good question. Actually, yeah, we haven't thought about comparing like noisy lines and noisy quantum circuit, like if they are the same depth. Yeah. Yeah.
I mean, I would have to think about how the noise model, what the noise model means when you have an oracle. I'm not sure. Is there a consensus on that even? Yeah. So I guess the answer is that I also haven't thought about it. The noisy case and an oracle separation. Yeah.
I mean, maybe you know, yeah, maybe the gates are faulty, but maybe you can assume that the oracle calls are clean. No, that's one possible model. Are there any other questions?
If we have a couple minutes left, I can show what the welded tree oracle problem looks like in one slide, you know, if anyone would be interested.
Sure, yeah, I think we have a couple minutes left, so go for it.
All right, I'll do that. Let's see here. But feel free to jump in with questions, you know, from the audience if you have any. Okay, yeah. So the Naihui, because we split 5 minutes, we Naihui explained the oracle that was used in their paper to find a separation between BQP and these bounded depth interleaved quantum classical classes. Sandketh and I actually used a different oracle separation, being kind of unaware of this other project. So we used this, what's called the welded tree oracle problem. Just a very brief overview, it has to do with having oracle access to this graph, to
Matt,
binary
we cannot see the
tree.
graph.
Oh, say again?
Matt, we cannot see the graph.
Oh,
Yeah, can you advance the slide, please?
oh, that's odd.
There, yeah,
Yes, good.
Now
Yeah, we're-
advanced?
yeah, we're seeing your PowerPoint window, not the
presentation.
slides.
All right, got it. I will just leave it like this then. Okay, so I think I'm out of time, but anyway, the welded tree oracle problem is a problem in which you have oracle access to this graph, and roughly speaking, the vertices have labels, and you're given the label to the entrance in the graph, and you're tasked with finding the exit, even though the graph is exponentially large. Now I'll leave it at that since we're out of time, but it's just a quick glance.
Okay, great. Thanks, Matt, and thanks to Naihui again. So let's move on to the final presentation of this session, which is by Carl Miller, who will tell us about the impossibility of efficient quantum weak coin flipping. So Carl, it's all yours.
Great. Okay, so I'm going to be talking within the domain of quantum cryptography, and we're going to be discussing two-party coin flipping, which basically means you have two parties who are cooperating but don't trust one another, and in this case, they want to generate a random bit, and Alice wants that bit to be 0, and Bob wants the bit to be 1, and they will do this by communication across a noiseless quantum channel. And then at the end of that communication, each of them will say what they think the outcome of the coin flip was. And so, so we want it to be the case that if both of them act fairly, you do get a coin flip that is fair and that they agree on. And we also want to limit the ability for a dishonest party to cheat. And the way we measure how good a protocol is through the bias, which is basically measuring the amount to which Alice or Bob could force the probability of their favorite outcome above 1/2. So the reason we call this weak coin flipping is because we are assuming that the favorite outcomes are known. If we did not know which direction Alice or Bob was trying to skew the results, we would call that strong coin flipping. However, strong coin flipping is already known to be impossible, so that's why we study weak coin flipping. Okay, so so the problem itself goes back at least to 1984 with Bennett and Broussard. Formal results started appearing in the 90s, and we had a series of results gradually improving the bias and also increasing the complexity of the protocols that we used, with the number of communication rounds also increasing as we went. And then we had this amazing results by Carlos Muchon from 2007, where he produced this 80-page paper with lots of inventive ideas. And he showed that you can actually bring the bias all the way down arbitrarily close to 0. He proved the existence of a family of protocols that accomplishes that. And that's been further developed by other authors since then. But curiously, there have not been improvements on the performance of the protocol. And that's unfortunate because this family was not an efficient family. And in fact, the number of communication rounds involved was exponential in 1/epsilon, where epsilon is the bias. So even though this is an amazing theoretical result, it's not really efficient or practical. And the central question that I'm trying to address in this work is the question of why in the last 13 years we haven't seen improvements to that figure. So in terms of what we have to go on, there's just this previous results by Andrus Ambenis, where he proved in 2004 that the number of communication rounds has to be at least log of 1/epsilon. So we have this slow growing function that at least guarantees we're not going to do better than, you're not going to get a constant number of communication rounds. But it leaves a wide range of possibility between log of 1 over epsilon and that exponential function that we were looking at on the last slide. And the optimal rate lies somewhere in between. So when I started this project, I was actually searching for efficient quantum coin flipping protocols because there was no reason at that time to think that they didn't exist. But here is the reality of it. It turns out that, so in this paper I was able to show that n, in fact, has to be greater than or equal to exponential of omega 1 over square root of epsilon. So this doesn't quite match that upper bound provided by Michon, but it comes pretty close. And basically what this establishes is an exponential number of communication rounds is necessary, and there's no way around that. And there's more details about the proof in my paper and in the longer version of this talk, but I will mention one of the key steps that I thought was kind of neat. So when I was searching for these efficient quantum coin flipping protocols, I was using Mathematica to do a numerical search, and it would never quite give me what I wanted. And eventually was able to nail down exactly what the obstruction was. So in order to achieve a fair coin flipping protocol, you actually need to have, you will need to achieve these rational functions that have this pinch shape that I show in the diagram here. So basically it's highly concentrated around 1 point and very close to 0 elsewhere. And I was eventually able to show that that is the only way that you can get a fair coin flipping protocol. And it turns out that you can prove using some complex analysis that the only way to get a rational function that has such a pinched shape is if the poles are exponentially large. And that exponentially large term translates directly back into the exponential lower bound on the number of communication rounds. And that's it. Thank you.
Great. Thank you, Carl.
Oh, I have a question.
Yeah, go for it.
Okay, yeah, this is super nice. Could you say more about what you mean about the rational functions result? What does it mean that a pole is exponentially large? You just mean like the height of the pole? Like, could you state that result more precisely?
Yeah. So so you can write these functions as a sum of rational functions where the denominator is linear. Mm-hmm. And then you have a term up above. So you have some polynomial function in the numerator. So I'm talking about the size of the pole is basically the value of that function at the pole. Mm. So if the denominator is x minus c, then I shouldn't use c, x minus r, then the size of the pole would be the value of the numerator at r.
Okay.
So J. Maurice Rojas asks also the residue then, I guess in response to what you're saying.
Yeah, I think that's, same thing as residue. Hmm.
So I have a more...
Oh yeah, go ahead, Henry. Sorry.
Oh yeah, I just had a general question, which was, are there other examples of primitives that you can't do exactly quantumly? I mean, for example, we know you can't do bit commitment information theoretically in the quantum setting, but is there like notions of weak bit commitment that you can do information theoretically, or other things like that?
That's a good question. I haven't looked into that. So I think so results that Henry is referring to. So there are known results that show that things like bit commitment can only be done with a fixed positive amount of bias. And the same is true for strong coin flipping as well. So in that case, there's like a certain threshold that we just can't go below. As far as I know, the case of weak coin flipping is somewhat unique in that we can go arbitrarily small, but we can't do it efficiently. But yeah, I mean, I guess we could, if we wanted to look for weaker versions of those cryptographic primitives, I guess that would involve choosing one of the constraints, the security constraints, and taking it away, and then seeing if we could solve that. Sounds interesting.
Yeah, Anurag, you had a question?
All right. Thanks, Henry. So, Carl, is the point game framework something very specific to coin flipping, or have people also generalized it to other cryptographic problems or communication problems?
It's a good question. So I think as it currently stands, it has mainly been applied to coin flipping. I suspect I'm interested in extending it to other possible cryptographic tasks, and I think that's an interesting avenue to pursue. So the point game formalism, I didn't have time to talk about it in this 5-minute sketch, but it is basically it's what's used in Michon's result and in my result. It's a way of formalizing a coin flipping protocol as a sequence of moves shuffling around points on a 2-dimensional plane. And that, it seems to me, is applicable to any situation where you have multiple parties and there's some number that each of them is trying to independently bound. Like in our case, Alice is trying to keep Bob's cheating probability down, and Bob is trying to keep Alice's probability down. And that's what leads to the 2-dimensional point game formalism. So I think there's hope that we could apply that to any such situation, where there's those balancing constraints.
So in communication complexity, which is more cooperative instead of competitive, you don't expect point games to be useful there?
I don't know. Yeah, it's I guess, I mean, if all parties are cooperating, it's less obvious to me, but yeah, it might take more searching.
Thanks.
Great. So that's it for the session. Maybe we'll turn off the recording now, and then for the next 20 minutes, I think we can just have like a free chat for whoever's interested, and whoever wants to stick around.